Hello, astronomy meteorology students. It's Mr. Johnson. Continuing our notes over properties of the atmosphere, I'll remind you that it's a great idea to jot down some information in a notebook or on somewhere on your Chromebook. So pause the video if you need to get that arranged. So let's talk about temperature. Temperature is what separates our atmosphere into different layers. If you look down at the bottom, troposphere is going to be the warmest at the bottom, and as you go higher into the troposphere, it cools down. When we hit the stratosphere, notice how that change in temperature is a new layer. So the stratosphere is going to be warmer as you increase in elevation or altitude. And that's due to the ozone absorbing UV light and heating up. Here again, we have a switch in temperature, a change in temperature, it decreases, and that decrease we call the mesosphere. And then we have an increase again in temperature, and that is going to be the thermosphere. So what exactly is temperature? This is probably going to be a fair amount of review, but I just want to clarify so that we have a common understanding. When we talk about temperature, really we're just measuring the amount of movement of particles. We're essentially saying how fast are they moving. Particles that are moving very fast, we call them hot, and particles that are moving slower, we call them cold. Now, these are all relative terms. In reality, we just have different levels of energy. And so hot and cold, they're just kind of our own perception of things. But the faster the particles move, the more they tend to spread out. This is very obvious with things like water. If you heat water up to the point where those molecules bounce into each other and spread out in all directions to take up the whole area that they can, we call that a gas, also known as water vapor. If you cool that gas down, those molecules don't move as fast and they tend to kind of cling together but not get stuck. They flow past each other. This is called liquid water, which is why we can take and we can cool water vapor in the air down. We can take energy away from that water vapor and it will turn to water in the form of liquid. If we then take away even more energy from that water, it will become a solid because the molecules will move slow enough that they'll lock into place. That's a basic idea of temperature. We can measure the movement of molecules in, different. We can use Kelvin, we can use Celsius, Fahrenheit. Science usually uses Kelvin or Celsius, and we commonly are probably more familiar with Fahrenheit, but just be aware of both of those. The energy can be transferred in the atmosphere, and it's this transfer that gives us our different weather patterns. I'm going to talk a little bit about energy transfer. I'll get into some details. You don't have to take notes over all of them. I'm just making you aware. I'll kind of glaze over some of the detailed notes. Basically, these particles are moving because they have energy, and that energy will move from an area where it's higher to wherever it's lower. Now, this is really obvious like when we go outside, for example. If you go outside and it's really, really cold out and you didn't bring a jacket, let's say you're shorts and a t-shirt and it's extremely cold out. Well, what's happening is those air molecules around you have way lower energy than your body. And so the energy moves from your body, to the air around you, which is why you start to feel really cold. Now, technically, you are heating up the air around you, but there's so much air that you're not going to increase the temperature really in any sort of measurable amount, just tiny bits. However, if we were back in school, there would be about 2,000 people in the building, and that's enough human bodies heating up the air around us that they actually account for that when it comes to the heating and cooling. Let's talk about how we transfer energy. There's radiation, conduction, and convection. We'll talk about all three here in just a minute. Again, I'm going to kind of summarize them, and you don't have to take real in-depth notes unless I suggest you do. To talk about radiation, radiation has to do with wavelengths of light of some sort of, so like electromagnetic radiation. We've talked about this already when it came to stars. What you need to know is that the energy on Earth, the vast majority of it comes from the sun. And it can travel in many different wavelengths. We just happen to see, the light, visible light. But there's other wavelengths too. There's X-rays and radio waves and UV rays and all that kind of stuff. It travels very quickly, and the wavelengths can change. When it comes to radiation, that light can be absorbed by the surface, and it could also be absorbed by the atmosphere. Now, in both situations, that absorption is going to heat things up. It's going to increase. So, like if that sunlight gets absorbed by the surface of the Earth, that energy gets transferred to the Earth, and then the Earth molecules move faster. Same thing with the atmosphere. Things like ozone, when it absorbs ultraviolet rays, it will, those ultraviolet rays, that energy gets transferred to the ozone molecules, and the ozone molecules move faster. And then they, in turn, can release that energy again in the form of heat. Something else that can happen is that energy can be reflected. So there is a certain amount of reflection because of the atmosphere, because of clouds in the atmosphere, and because of surfaces on the Earth, like, for example, snow is really good at reflecting light. And so essentially the rates of absorption really depend on what is what the light is striking, what it's hitting. Talk about conduction. Conduction is when energy transfers because of direct contact. It happens best between solids and liquids, or in solids and in liquids. A really easy example is if we're boiling water on a stove, the heat source on the stove, that energy gets transferred throughout the whole container that we're, throughout the whole pot that we're boiling the water in, to the point where you might touch a metal handle and the handle's hot. Well, the handle's not hot because it had direct contact with the heat. Instead, the energy has traveled through conduction through the pot and has warmed up the handle. The atmosphere tends to be a really poor conductor in terms of conduction. So really, it's mostly gas. The atmosphere is made of gas, and so conduction doesn't happen very well. It can, but it doesn't happen very much. It does happen between the Earth, where there's energy, and the air above the Earth. And so kind of the lower parts of our atmosphere can absorb the heat or the energy from the Earth itself. And that's how we can get warming of air just above the Earth's surface. Convection. Convection is the movement of a fluid, either gas or liquid. And the majority of what we're going to be talking about has to do with convection in our atmosphere. The basic idea that we just talked is through convection, the Earth can warm the air just above it. Well, what happens to that warm air? We know that things that are warmer have more energy and spread out. That means that warm air is less dense and it tends to rise. As gases cool, they become more dense and they sink. And so we have the situation where air can have different densities. And it just so happens that when air is warm, it expands, becomes less dense, and arises. It kind of floats above the more dense air. If the air cools down, it condenses, it gets tighter, kind of more compacted, and it sinks. And so because of that, we sort of get this mixing up and down and up and down. Now, this is a really common thing throughout science. You'll see it all sorts of different ways, but we're going to be talking about convection in our atmosphere. I'll take just a minute and remind you that you can see this when you boil water. Just before the water starts boiling, take a look at it, and you'll see that there's heat, warm water is rising, and the relatively cooler water is sinking, and we get this kind of churning effect. A little bit more about, so a question I have for you is, just a minute ago, we mentioned that two things. One is that higher up in the atmosphere, in the troposphere, it's cooler, but we also just mentioned that warm air rises. So why is it colder at higher temperatures? I thought I just said that warm air goes up and cool air sinks, so it shouldn't be the other way around. Well, that would be the case if everything is kept constant, but it's not. As hot air rises, it finds itself in an area of decreased pressure, less pressure, as we talked about in the last video. So when that hot air rises, it expands. And when you expand gas, it cools down. You can demonstrate this pretty easily by taking a spray can, like an aerosol spray can of some kind, paint or hairspray or whatever, and you spray that spray paint, you spray that hairspray, and if you spray it long enough, the container will actually physically get cooler. It's because you're taking that material and you're letting it, you're decreasing the pressure inside, and that gas will actually cool down. So that's why we get it's cooler higher up, because of that decreased temperature. Decreased pressure. So sometimes we can have a break from the normal, where ordinarily it's cooler higher up. Sometimes we can actually have a trapped layer of cold below. Under normal circumstances, hot air rises, and then that cool air will sink and heat up again and rise and sink. You can see the picture at the bottom. That sort of mixes everything up. Sometimes, though, we can have a layer of cold air that's trapped under the warm air. This is called temperature inversion. The things that can cause that is if we have rapid cooling off of the land. So here we have ordinarily this whole thing would be warm, and if that cold air, or if the layer close to the Earth in some way is able to cool down, like at night when it is able to rapidly cool, we might have a layer of warm air above that newly cool air. Another thing that can happen is we have these things called air masses. An air mass essentially is this big, giant pocket of air, really, really large, that has similar temperature and similar amounts of moisture in it. If we have warm air that's less dense, and if it encounters cold air that is more dense, that cold air will stay closer to the ground, and the warm air will move up over top of it. That's another way we can get this temperature inversion. Either way, temperature inversion is where the lower layer is cooler, and then we have a warmer layer above in our atmosphere. Now, what that can do is that because we don't have mixing, we tend to have a lot of pollution can be trapped thanks to this temperature inversion. So again, normally warm air rises, cool air sinks, and we get to mixing. Well, if we have a trapped layer of cold air, it's just going to stay there, and the warm air is going to not mix with it. So things like exhaust and air pollution and any of those other kinds of pollution that would be in the air are not able to escape, and even sometimes forest fires can cause some smoke that will be stuck in this temperature inversion. Another thing that can happen is we can have fog or low-level clouds that might form there because it's cool enough for condensation to happen. It can cause air pollution problems, and ultimately that can be fixed when there is a return to normal in terms of that atmospheric layering. Now let's combine air pressure and temperature and see how they affect each other. The Earth is not evenly heated, and because of that, what we have is we have areas where there's warmer air and areas where there's cooler air. Now, what that does is that causes us to have different densities of air. We have cold air that has a higher density, and we have warm air with a lower density. And so that air will move from where there's a lot of it, where it's more dense, to where it's less dense. In other words, we tend to have movement from where there is cooler air to where there is kind of warmer air. And that has to do with pressure. So there's more pressure in cool air, and there's less pressure in warm air because they are different densities. This causes wind. This movement from high pressure to a low pressure is wind. So that's really what's causing things to the air to blow around you. We can think about the sea, for example. Oftentimes the sea is colder than the land. The land heats up so that air becomes less dense and rises. The cool air is more dense, and so it flows into where there is warm air that's rising. That's why we can get these coastal breezes. That wind speed can change with altitude. It tends to blow faster further up because it doesn't come in contact with as many things. It moves faster in flatter terrain. Think about South Dakota. And it really has to do with friction. So I'm going to leave that with, I'm going to stop the video now. There's a few Edpuzzles to watch. Thanks for taking time to take notes, and I will see you in the next video.